Good morning, students. In this video, we are going to continue the last session, nothing but memory banks. So, as we know that the memory bank, there are two types of banks. One is the lower bank and the upper bank. Lower bank is called as a even bank, and upper bank is also called as a odd bank because it is holding the odd addresses. So, holding the odd addresses means it is differentiated with the help of the chip enable signal. As we know that the even bank is connected to the lower order data bus and upper bank is connected to the higher order data bus. Lower bank is connected to the even lower order data bus. Upper bank is connected to the higher order data bus. Okay. Now I would like to read 8-bit information. I would like to read 8-bit information from the microprocessor. Now I would like to read 8-bit information from the microprocessor. I would like to read 8-bit information from the microprocessor using the direct addressing mode of operation. For that, I am writing the move al, square bracket 1234h square bracket 1234h. So this is an example which is there in your textbook. If you are going through the textbook, and the same example we took during the explanation of our direct addressing mode of operation in the during the addressing modes explanation in 8086 microprocessor. So what is the meaning of this one? So the microprocessor reads the data. Microprocessor reads the data from the 1234h offset address into the AL register. From the 1234 offset address into the AL register. Okay now. So it is this 1234h is a even address na, even offset address na, means this address belongs to the even bank. Here are somewhere this address is existed. Okay now. So this address belongs to the even bank. Okay. Now when you are writing this instruction, the microprocessor, you are clearly mentioning that I would like to read the 8-bit data because the destination size is 8-bit now. So the microprocessor reads the 8-bit information from the 1234h memory location into the destination register. So when you are reading the data from the even memory location, that is the even bank, obviously the data is going to be passed through. It is passing through the lower order data bus. It is passing through the lower order data bus to the microprocessor. I am assuming that here we are having the microprocessor. Okay, now here we are having the microprocessor. Let us suppose I am having one more instruction. I would like to write the one more instruction, which is a bx comma square bracket 1234h 1234h. So here in this case the difference between these two is, in this case the destination size is a 16-bit register. The destination size is a 16-bit register. Means we are asking the microprocessor to read the 2 bytes of memory location from the memory, specified memory, 2 bytes of memory, because each memory location is holding the 8-bit information. Okay now. So in order to read the 2 bytes of information from the 2 memory locations, obviously, so here it is a 16-bit number. Now 16-bit number means we are having the higher byte as well as the lower byte. So in the memory, whatever the address you are specifying as a part of the instruction, this address is specifying the lower order byte of the 16-bit number. Lower order byte of the 16-bit number means 1234h. The microprocessor reading the data from the 1234h as well as 1235h memory locations. Okay now. Microprocessor reading the data from the 1234h location as well as from the 1235h location. Okay now, 1234h location will be read into the or I can say that it is copied into the BL register, and 1235 location data copied into the BH register. As I told you that whatever the lower order address we are having, whatever the address you are specifying as a part of the instruction, that is specifying the lower order address, lower order byte address. Lower order byte address means the information available in this memory location copied into the BL register. The information available in the next higher order memory location will be copied into the higher order byte. Okay. So commonly it is forming the 16-bit number. Commonly it is forming the BLBH. Commonly it is forming the 16-bit number. Okay. Now it is forming the 16-bit number. Now in order to perform this operation, what the microprocessor will do means the microprocessor will read the 1234h data from the lower bank because it is a even address now. So it is reading the information from the lower bank using lower order data bus. Using lower order data bus to the microprocessor. Okay now. And microprocessor reading the higher order byte, which is the odd address now. So means one byte is read from the even bank and another byte which is the odd address read from the upper bank, that is nothing but the odd bank, using the higher order data bus, into the microprocessor. So one is from the lower order data bus and another one is from the higher order data bus. So means here the whatever the data bus we are having, it is trying to carry the valid information. Means lower order data bus is always carrying the lower byte of the information, higher order data bus is always carrying the higher byte of the information. Okay, are we clear? So lower order data bus, which is a D0 to D7, is carrying the lower order memory location, and higher order data bus is carrying the higher memory location, that is nothing but the higher byte information. Okay, are we clear? So this is what we are having. Let us suppose if this offset address is not the even number, then what will happen? Okay, now what will happen is a question. So before going to the before going further, means before going to the odd addresses instead of the even address, if we are taking the odd address, before going to that, what we do is we'll concentrate on, in order to perform the read write operation, what you are supposed to do, you are supposed to place the address on the address bus, generate the A 0 signal. When you are generating the A 0 signal, lower bank is going to be enabled. When it is enabled, the data which is there in the 1234H memory location, it will be placed on the lower order data bus, and that will be driven to the microprocessor. In the next means, soon after the microprocessor reads the information from the lower bank, immediately it will generate the BHE bar also, because we are interested in the 16-bit information. So when the BHE bar is enabled, A0 is going to be disabled now, because A0 is disabled because of 1235H. In the 1235H, A0 position is a 1. So when it is a 1, obviously this one is going to be disabled and this one is going to be enabled, and the higher order data bus is placed on the higher byte value is placed on the higher order data bus, and it will be read into the microprocessor. Okay, means the information is passed, the 16-bit information is passed in the lower order format as well as the higher order format. No confusion at all. So if at all we are having the offset address is an odd number, if the offset address is an odd number, then what will be the problem is a question. So if you take see 8-bit number, no problem at all. If you take the 8-bit number, let us suppose 1237H. I am taking the 1237H as an address, offset address. So in this case, what will happen? We are interested to read the data, which is a 8-bit data, because the destination size is 8-bit data. So microprocessor reads the 8-bit data from the odd bank, not from the even bank. Previously it is from the even bank, now it is from the odd bank. So means now the higher order data bus is used to read the data from the memory location into the microprocessor. Now, if at all we are having the situation like this, let us suppose I am having the BX comma, instead of the offset even address, if I am having the odd address, just like the previous one. Previously we are having the even address, now we are having the odd address. So in this case, what will happen, lower order byte is read from the 1237H location, and the higher order byte read from the 1238H location, because two consecutive memory locations are used to hold the 16-bit number, or with respect to this instruction I can say that two consecutive memory locations are read from the memory, means the values are going to be 2 bytes of information read from the memory, which is specified over here, into the BX register. So that value is nothing but whatever the offset address we are having, as we know that it is showing the lower order memory location. Higher order memory location is nothing but the next higher memory location. Okay. Now in this case, if you observe this one, BL is carrying what, BL is carrying the lower byte. BH is nothing but the higher byte. But the BL address is what, 1237H. So when you are carrying the 1237H, which should be what? Lower byte. But lower byte information should be read by whom? Read by the lower order data bus. It should be read by the lower order data bus. But unfortunately, as we are having the odd address, now the information should be read from where? Should be read from the 1237, which is nothing but the odd bank. As a means, here the higher order data bus is used for carrying the lower order data. Lower order data. So means there is a mix up. When we are having the odd address over here, at that time, the higher order data bus is carrying the lower order byte. Lower order data bus is carrying the higher order byte. Okay, now lower order data bus is carrying the higher order byte, which is nothing but the higher byte, and lower order data bus, higher order data bus is carrying the lower byte. Higher order bus is carrying the lower byte. Higher order bus is carrying the lower byte. So conflict. So means when you are giving the, why I am specifying this one means, if you are going to in the table, you are the operations, in order to perform this operation as well as in order to perform this operation, the microprocessor is going to take only one clock cycle. But in order to perform this operation, in order to perform this operation also only one clock cycle. But in order to perform this operation, the microprocessor is taking the two clock cycles. Microprocessor is taking the two clock cycles. I think during the explanation of direct addressing mode of operation, I would have explained that the even address, if the offset address is the odd address, if the offset address is the odd address and you are trying to read the 16-bit information from the memory, at that time microprocessor takes the two cycles, two bus cycles. Okay, now why it is taking the two bus cycles? Actually lower byte should be read, lower byte should be from the even bank, higher byte should be from the upper bank, because the lower bank is lower byte of the 16-bit number pass through the lower order data bus, but higher byte of the 16-bit number pass through the higher order data bus. But here lower byte should be lower byte should be transferred using the higher order data bus, not the lower order data bus. And higher byte should be transferred using the lower order data bus, not by the higher order data bus. Means the situations are changed. So that's why when the microprocessor is performing the reading operation, means when the microprocessor is reading the lower order byte from the memory location, it is not performing the reading operation from the higher order byte, which from the higher memory location, because there is a conflict. Why conflict? In general, lower data is going to be read through the lower order data bus, higher byte information read through the higher order data bus. But here higher order data bus is used for carrying the lower order byte, and lower order data bus is used for carrying the higher order byte. That's why it is taking the two clock cycles. That is the two machine cycles, not clock cycles, two bus cycles if you want more specific. So based on that, if you see this one, look at this. This is what I would like to express. Okay, so here when we are having the, what are the signals which we are seeing in the previous diagram slide, which is the A0 BHE bar memory bank, whether the bank is a even bank or the odd bank, and the higher order data bus and the lower order data bus and the higher order data bus. If you see this one, I would like to read the data. I would like to read the data that is in the byte format, only 8-bit information from the even bank, or I would like to write the data onto the even bank. So in order to enable the even bank, A0 bit position should be the 0, because it should be active low. Okay, now I can't go back every time. Okay, otherwise I'll go back to the, so here if you want to read the information from the what is that even bank, it should be chip enable signal should be enabled. For that A0 should be enabled. So that's why it is active low. And as we are performing the byte information operation, odd bank is going to be disabled by applying the high. Okay, now the active memory bank is a even bank, and data is passed through the lower order data bus, and the higher order data bus in the tri-state mode, because we are performing the byte operation. Let us suppose if we are performing the word operation and the address is the even address, then both signals A0 BHE bar, means the lower bank as well as the upper bank, both are activated in parallel, and the information is read from the even bank as well as the odd bank. And now these two bytes of these two data buses, that is a higher order data bus and lower order data bus, both are carrying the valid information. If we are trying to perform the byte operation with respect to the odd address, then odd address means it belongs to what? Upper bank. Okay, no need to concentrate on the lower bank for the byte operation. So that's why A0 is a 1 and the BHE bar is made as a 0, and bank with which we are really performing is a odd bank. And obviously when we are using the odd bank, nothing to do with the lower order data bus now. So tri-state, this particular lower order data bus in the tri-state mode, and the higher order data bus is carrying the valid information. Now the thing is, if we are would like to perform the word operation, means we would like to read the data in the word format, not in the byte format. So what is the problem? If the starting address, whatever the address which we specified as a part of the instruction in the previous, again, just few minutes back, so that address, if it is an even address, sorry, if it is an even address, sorry, in order to perform the word operation, if it is an even address, then only one bus cycle is enough. But if it is an odd address, conflict is what? During the first clock cycle, during the first cycle, we are reading the information. Lower byte is read from where? From the upper bank, not from the lower bank. So that's why it is disabled by applying the high, and it is enabled, and the information is carried from the transfer from the, what is that, memory bank, that is the odd memory bank, and obviously lower order data bus is disabled because it is a tri-state mode and it is having the valid information. In the next bus cycle, in the next bus cycle, we are reading the lower order higher order data, that is the higher byte from the lower bank, higher byte from the lower bank, okay, higher byte from the lower bank. So because of that, this one is a low and this one is high, and this one is a even, memory bank is the even, and this is the data which is carrying the higher order byte. Actually higher order byte should be, in general, higher order byte should be transferred by the higher order data bus, lower order byte should be transferred from the lower order data bus using the lower order data bus, but it is not happening when you are taking the offset address is a odd address. If it is the odd address, obviously microprocessor is taking the two bus cycles to perform the word rewrite operations, to perform the word rewrite operation. Okay, this is what we are having. Okay, if you want to realize this one, generally if you are taking the 16-bit number, in that 16-bit number we are having the lower byte and the higher byte. Lower byte should be transferred by the lower order data bus, higher byte should be transferred from the higher order data bus, because the data bus is a 16-bit number now. So when you would like to read the 16-bit number, so obviously lower order data byte should be from the lower order data bus, higher order data byte should be from the higher order data bus. But if you are not having the even bank, if you are not giving the even bank as an offset address, obviously there is a confusion is, there is no confusion actually, but the microprocessor is taking the two bus cycles instead of one bus cycle, instead of one bus cycle. Okay, so the next concept is, yeah, we are supposed to concentrate on address decoders. We are supposed to concentrate on the address decoders. Okay, so I told you that yeah, wait a minute, we have seen the memory. Yeah, with this diagram, memory banks concept is over. One of the long question. Okay, memory banks, they may ask you explain the memory banks in your 8086 microprocessor. Then simply you can write that the microprocessor mapping the memory to the memory space, space by treating the memory as a even bank and the odd bank, even bank is carrying holding the even addresses, and the odd bank is holding the odd addresses. Okay, now so like that you are supposed to explain. After that you are supposed to draw this diagram, whatever the diagram which we are having on the screen. You are supposed to draw this diagram with all the signals, and you are supposed to explain with this table, this table. Now let us suppose I would like to interface my memory device to the microprocessor. So we have seen the banks concept. It is a concept. Okay, now it is a concept. Now I would like to what to interface the memory device to the microprocessor. Interfacing the memory devices to the microprocessor is nothing but mapping the memory devices, mapping the, wait a minute, mapping the memory devices into the memory space provided by the microprocessor, mapping the memory devices into the memory space provided by the microprocessor. Okay, wait a minute, let me take one thing. Okay, so as we have seen in the last class, means not in the last class, in the previous classes, I told you that the microprocessor is providing the 20-bit address for bus for the memory devices and 16-bit address bus for the IO devices. Okay, now so if I'm taking it as a 8086 microprocessor, it is a 8086 microprocessor. As I told you that it is providing the 20-bit address bus for the what is that, 20-bit address bus, is providing the 20-bit address bus for the memory devices, and the 16-bit address bus for the IO devices. Okay, 16-bit address bus for the IO devices. As we are having the 20-bit address bus, it is providing the 1 MB memory for the memory devices. Means it is providing the 1 MB size of memory. It is providing 1 MB space, 1 MB space for the memory devices, and 64 kilobytes of space for the IO devices. Okay, so whenever you would like to interface the memory devices, that memory should be mapped into the memory space provided by the 8086 microprocessor. That memory space is nothing but the 1 MB. But if you want to map the memory device, means if you want to interface the memory device, this is a memory device. If you want to interface this particular memory device to the microprocessor, means you should perform the mapping operation. So mapping is going to be done with the help of the address decoders. Mapping is going to be done with the help of the address decoder. As an example, in this video, I am going to take one simple explanation how we can interface the memory device to the microprocessor. The other way of explanation is how we can map the memory devices into the memory space provided by the microprocessor with the help of the address decoders concept. Okay, so in this video, we are going to study about how we can map the memory device into the memory space provided by the microprocessor using the address decoders. We are not concentrating on the IO map. We are not concentrating on the IO map. We are concentrating only on the memory map. Okay, so means we are mapping the memory devices into the memory space provided by the microprocessor. We are not dealing with the IO devices because we are not interfacing the IO devices right now. We are trying to interface the memory devices to the microprocessor. Mapping is done with the help of the address decoder. Mapping is done with the help of the address decoders. Okay. So let us see the diagram. Okay. Let us see the explanation of that particular mapping operation. So here, as I told you that 8086 microprocessor is providing the 1 MB memory size. Okay. 1 MB memory space to map the memory devices. Okay. 1 MB memory space to map the memory devices. Okay. So this is the 1 MB memory space, okay, provided by the microprocessor to map the memory devices. As we know that the space, whatever the space which is provided by the microprocessor is there, na? So microprocessor is providing the 1 MB space. Na? This space is virtually splitted into the blocks format. That block is called as a segment. Na? We have seen that concept. Okay, na? So this memory space is virtually divided into the blocks format, and each block is called as a segment. How many segments are there? 16 segments are there, like this. Okay, so we are having the 16 segments. I am naming those segments as a segment 1, segment 2, segment 3, segment 4, and so on, segment 16. Total 16 segments are there. Total 16 segments are there. Okay, now. So each segment size is how much, ma? 64K. Each segment size is a 64K. Okay, so don't get confused. Order is 8086 microprocessor is providing the 1 MB space and the 1 MB space to interface the memory devices, and in that particular 1 MB space virtually divided, logically divided or virtually divided into the 16 blocks, and each block is called as a segment. Each block is called as a segment, and each block size is a 64K. Each block size is a 64 kilobyte of memory. Let us suppose I would like to take one means in the market I am having only 164 kilobyte of memory. I'm having only 164 kilobyte of memory device. Means I would like to interface the 164 kilobyte of memory device to the microprocessor. 164 kilobyte of memory device to the microprocessor. Okay. Now. So assume that this is my memory device whose size is a 64 KB. As we know that for means during the explanation of the memory concept, we are having the two types of memories, na, ROM as well as the RAM. ROM device is having the two control signals. One is the chip enable signal as well as the output enable signal. RAM is having the three control signals: write enable signal, output enable signal, as well as the chip enable signal. But in order to avoid the complexity of interfacing diagram, I am not considering the rest of the control signals like output enable and the write enable signals. I am just taking only the chip enable signal. Remaining control signals also existed, but in order to avoid the complexity of the interfacing diagram, I am not considering them. Okay. So now, when you would like to interface this particular 64 kilobytes of memory space to the microprocessor, as I told you, what we are supposed to do, we are supposed to map this particular device into the one of the segment block, one of the virtually splitted segment block. That is going to mapping this memory to the memory space provided by the microprocessor is going to be done by whom? By the address decoder. But before that, what is the size of this particular memory device? 64 KB. In order to access the 64 KB, how many address lines we require? How many address lines we require? 16 address lines we require. In order to access this particular 64 KB memory location, memory device, we require the 16 address lines, along with each location is holding the 8-bit information along with the data bus. So I'm assuming that this data bus as well as the address bus are coming from the microprocessor. Or I can say that this particular memory device requires the two buses. One is the address bus, another one is the data bus. Data bus is nothing but it is a 8-bit data bus, and address bus is a 16-bit address bus. Why this device expecting the 16-bit address bus? Because whose size is a 64 KB. Whose size is a 64 KB means this particular memory device is having the 16 address lines as well as the 8 data lines. And now, in order to map this device into the memory space provided by the microprocessor, we require one more device called as a address decoder. We require one more device called as a address decoder. Okay, now so here we are having the different types of address decoders we have seen in the previous classes, but now in this case I am considering the 74LS138. I am considering the 74LS138 address decoder, which is a 3 to 8 line address decoder. I am considering the 74LS138 decoder, which is a 3 to 8 line decoder. So 3 to 8 line decoder means we are having the three inputs and 8 output lines. Along with these 3 inputs, we are having the 3 control signals also. These are the control signals of the what is that address decoder. Now, in order to map this particular memory device into the memory space provided by the microprocessor, what we are supposed to do means we are supposed to make use of the address decoder. Okay, now we are supposed to make use of the address decoder. When you would like to make use of the address decoder means when you would like to use the address decoder to map this particular memory device into the memory space, what you are supposed to do means you are supposed to concentrate on the chip enabled signal. Means you are supposed to make use of one of the output line of the address decoder, connect to one of the output of the address decoder as an input to the chip enabled signal of the memory device. When you are connecting one of the output line of the address decoder to the chip enabled signal of the memory device, then you are mapping this one. You are mapping this particular memory device into the one of the segment provided by the microprocessor. This is the space provided by the microprocessor, and whatever the division we are having, it is a virtual division. For your sake, I divided this one into the virtual format. Okay, now so when you are connecting one of the output line of the address decoder to the chip enabled signal, then this memory device will be mapped into one of these segments. To which segment it is mapped, we will see that one. To which segment it is mapped, we will see that one. Okay, now so as of now I would like to map this one. Now in order to map this memory into the memory space, I am going to connect one of the output line of the address decoder to the chip enabled signal of the my memory device. Okay, now chip enabled signal of the my memory device. In these out of 8 output lines from this particular address decoder, I am taking the Y0 output line. Means I am using the Y0 output line as an input line or as a chip enabled signal to the this particular memory device. Okay, now this particular memory device. But if you are giving the connection like this, if you are giving the connection like this, if you are giving the connection like this, okay, now if you are giving the connection like this, what will happen? sorry, audio was locked. Okay. So here where we are, yeah. In order to map this one into the memory space, what I'm doing is I'm connecting the one of the output line of the address decoder to the chip enable signal of the memory device, chip enable signal of the memory device. And in order to choose one of the output line, we are supposed to give the proper input combination. We are supposed to give the proper input combination. Which signal we are supposed to use in order to supply the input signal in order to drive these three input signals, which signals or which signals from the microprocessor should be used to drive these three input lines in such a way that it is going to be select the why not output is a question. Okay, now why not output is the question. Now here there is a tricky point plays a major role. There is a tricky point plays a major role. So from the 8086 microprocessor, how many address lines we are having? From the 8086 microprocessor, we are having the 20 address lines. Okay, now they are starting from the A0 to A19. They are starting from the A0 to A19. 20 address lines are there. So out of these 20 lines, from here onwards, remember, whenever you would like to interface the memory devices to the microprocessor, see whatever the mapping space I'm providing over here, it is only for realization process. Okay, now. So as we move on, this space is going to be eliminated. It is only for the realization process. I took this middle way. Okay. So here, whenever you are interfacing the memory device to the microprocessor, whenever you are interfacing the memory device to the microprocessor, whenever you are interfacing the memory device to the microprocessor, you are supposed to know how many address lines are required by the memory device. So as per this memory device, it requires the 16 address lines. So that's why we are going to take 16 address lines from the microprocessor. The microprocessor means the 16 address lines of the microprocessor are directly connected to the address bus of the memory device. They are directly connected to the address bus of the memory device. Okay, now remember, allocating the address lines to the memory device is always done from the right to left format. Means you should move from the lower order, that is the LSB bit of the address line to MSB bit of the address lines. Okay, now LSB bit to MSB bit. You are not supposed to move from the right to left format. You are supposed to move from the left to right format. So this, in order to interface this memory device to the microprocessor, how many address lines we required? 16 address lines we required. These 16 address lines are taken from the 20-bit address bus of the 8086 microprocessor. So how many lines are directly connected to this particular memory device? 16. Now how many address lines are left, 8 address lines are, sorry, 4 address lines are left. We left with the 4 address lines. Now in order to choose one of the output line, in order to choose this particular output line, we are supposed to give the proper input combination to this particular input lines now. So that is going to be done with the help of the remaining address lines which are there in the 8086. Okay, now. So how many lines we require? 3 more lines. Means the A16, A17, A18 lines are going to be connected. They are connected as an input lines to this particular address decoder. Let us see the next slide. So look at this one. In the next slide, what I'm doing is I'm simply taking the A16 to A16, A17, A18. A16 as an input line to the A17 as an input line to the B, A18 as an input line to the C. Remember, here A in the ABC, C is the most significant bit and A is the least significant bit. That's why I'm taking the least significant bit of the address line to the least significant bit, most significant bit of the address line to the most significant input line of the address decoder. Okay. So here, how many address lines we used till now? How many address lines we used? Totally 19 address lines we used, because from the A0 to A15, from A0 to A15 are directly connected to the address lines of the memory device, and remaining how many left? We left with the 4 na. Out of these 4 lines, 3 lines are used as a input lines to the address decoder. These three lines are used as a input lines to the address decoder. Those are nothing but the A16, A17, A18. Even though we have the proper input combination, why we are taking these input lines? Because in order to choose one of the output line, we are supposed to give the proper input combination. Even though we have the proper input connection, in order to get the functionality from this particular address decoder, we are supposed to activate the enabling signal, that is the control signals of this particular address decoder. We are supposed to enable the we are supposed to activate or enable the control signals of this particular address decoder. So this 74LS138 address decoder is having the three control lines. One is the active high line and remaining two are the active low lines. One is the active high line, remaining two are the active low lines. Okay, now active low lines. Now if you want but how many control lines we are having? How many enabling signals are there for this particular address decoder? Three signals, but we left with only one address line. We left with only one address line. It is up to you. You may use the A19 to enable the G1, or you may use the A19 to enable the G2 A bar, G2 B bar. That is the active low signals. Okay, now. So depending on the mapping, depending on the enabling connection, depending on the A19. Come on, man. This pointer is not showing. Okay, so depending on this particular A19 position, whether you are using the A19 to enable the active high signal or to enable the active low signal, this memory device may be mapped to the segment 1, that is the initial segment positions, or may be mapped to the final segment positions. Okay, now let me show you how. Let us suppose I am using the A19 to activate the what is that active low signals of the address decoder. This pointer is not working fine, right? Okay, so to activate the active low signals of the address decoder, I am using the A19. G1 is the active high signal now, so we are not having the spare address lines. Okay, now all are used. So that's why what I'm doing is I'm connecting the active high signal directly to the G1 by applying the VCC. I'm directly connecting the VCC to enable the active high signal of my address decoder. Now, what will happen? So we are enabling this particular address decoder by using the active high signal as well as the active low signal provided by the A19 address line. And these three lines are used for what? Enabling the one of the output line. But in order to get the Y0 output line, what you are supposed to do? You are supposed to give the 00 bit combination at the input lines, because 000 is nothing but the Y0, 111 is nothing but the Y7. So like that we are having all the combinations. I am not revealing that one again. Okay. So now, so here if you are giving this kind of connections, then your memory device is successfully mapped into the memory space. It is successfully mapped into this particular memory space. By whom? By the address decoder. By this particular address decoder. Means interfacing the memory device to the microprocessor is nothing but mapping the memory device into the memory space provided by the microprocessor. That is the one way of explanation. And another way is, when you would like to interface the memory device to the microprocessor, first of all you should focus on what is the size of the memory device. So if it is a 64 KB, so in order to access the 64 KB memory size, how many address lines we require? 16 address lines. So as we require the 16 address lines from the 8086 microprocessor, you are supposed to use the 16 address lines and connect to those address lines directly to the memory device. Now, in order to map this particular memory device to the microprocessor, or in order to interface this particular memory device to the microprocessor, what you are supposed to do means you are supposed to enable the chip enable signal of your memory device. You are supposed to enable the chip enable signal of your memory device. Further, what you are supposed to do, you are supposed to use the address decoder. You may use the 74LS139 also, which is a 2 to 4 line decoder. But for my convenience, what I am taking is I am taking the what is a 3 to 8 line decoder, which is nothing but the 74LS138. Okay, 74LS138. I am going to make use of one of the output line of the 74LS138 to enable the chip enable signal of my memory device. In order to choose one of the output line, you are supposed to give the proper input combination to this particular address decoder. So that input combination should be they should come from the address lines of your memory address bus coming from the microprocessor. So three address lines of your address bit positions coming from the microprocessor are used as a input lines. Okay, but if even though we have the input combination, we are not going to get the functionality, because we are supposed to enable the activating signals of this particular what is that 138 that is a address decoder. So one is the active high signal, directly I am applying the plus VCC, and I am using the A19 line to activate the active low signals of the 74LS138. Sorry, 139. Sorry, it is a 138 only. In order to activate the active low signals of the 74LS138, I am using the A19 line. So this is the means with this diagram. If you see this diagram, this is the interfacing diagram to map your memory device into the memory space provided by the microprocessor. Now the question comes that, okay, so each memory space, each memory block, each block is a 64 KB. So successfully we can map this particular memory device into the segment 1 or segment 2 or and so on to the segment 16. So based on this construction, whatever the connections we are having, based on this particular interfacing diagram, where exactly this particular 64 KB is going to be mapped. Means whether it is mapped into the segment 1 or segment 2 or segment 3 or segment 4. Mapping this particular device into a particular segment can be decided by the address lines as well as the output lines. Output lines of the address decoder. Means if you change the output line, let us suppose I am going to use the Y3 output line from the address decoder. Then mapping of this particular memory device is going to be changes to some other segment, not into the first segment. If you are taking the Y0, it is mapped into the first segment. But if you are taking some other number, so some other number means some other number, then obviously the memory device is going to be mapped to the some other segment. Okay, so means based on the output lines of your address decoder, mapping the memory device into a specific block, that is a segment, is going to be changes. It is going to change. Now let us see, based on this particular construction, what is the address, means to which segment this particular memory device is mapped is a question. This particular memory device is mapped is the question. Before going to that, what we do is we will concentrate on the address bus. Sima, how many address lines are there for this particular address bus? 16 address lines are there. They are coming from the microprocessor, no problem. Okay. So using the 16 address lines, we are going to have the 2 power 16 combinations now. Means all zeros to all ones now. What I mean to say that if you are taking the what is that? Yeah, if you are taking the 3-bit number for convenient, if you are taking the 3-bit number, 3-bit number means we are going to get the 8 combinations, 000 to 111. Like that, if you are taking the 16-bit number, then it is varying from 16 zeros to 16 ones. What I mean to say that, look at this one. Look at this. Okay, so whatever the memory device we are having over here, what is our interest? Our interest is based on this connection, this particular memory device is mapped into which segment is a question. Okay, now in order to know that one, first you are supposed to focus on the address lines. So what are the address lines which are interfaced to the memory device directly? 16 address lines. They are varying from A15 to A0. And now this bit combination is varying from the minimum to maximum bit position. It is varying from minimum to maximum. Minimum is nothing but the 16 zeros. Maximum is nothing but the 16 ones. Minimum is nothing but the 16 zeros. Maximum is nothing but the 16 one. This is the address range of the memory, this memory device, because it is a 64 KB. Now, to which segment it is mapped is the question. Na? So, in order to differentiate that one, you are supposed to focus on the Y0 bar. You are supposed to focus on the Y0. In order to enable the Y0, what you are supposed to do? You are supposed to apply the binary 0 over here. You are supposed to apply the binary 0 to this one, as well as to this one, as well as to this one. Means if the 3 input line status is a 0 0 0, then output is a Y0. From the truth table of the 74LS138, you can get the information. Okay, so if you are applying the 3 zeros at the input of the address decoder, then output is the Y0 output line. We are having the 8 output lines. Out of 8, Y0 is going to be enabled. It is enabled. Y0 is enabled. But in order to enable the Y0, along with these input combinations, you are supposed to activate the activating signal. Now, one of the activating signal is already activated, and another activating signal is the active low signal. Now, you can activate these active low signals by applying the binary 0. So, by applying the binary 0. Okay. So, means when you are applying the A19 bit position as a 0 and A16, A17, A18 position as a 0 0, then this particular address decoder is mapping your memory device into the segment 1, into the segment 1, into the segment 1. Okay, into the segment 1. So here this one is what varying from the minimum to maximum. Memory device is varying from minimum to maximum. Throughout the combinations, throughout the minimum to maximum combination, these 4-bit position should be always 0, because if we are not having the 0 0 at the input of these means if the for three signal status is not the three zeros, then obviously if these three signal statuses are not the three zeros, obviously the y naught is not going to be selected. If you want to select the y naught, these 3 bit positions should be 0, and in order to get the functionality from this one, the A19 bit position should be 0. That's why it is always 0. So means from in the minimum combination it is 0, in the maximum combination also in the 0. Now let us see what is the address range which is allocated for this one. So here we are having the 16 segments now. Let me go back. Here we are having the 16 segments now. Okay, 16 segments. 16 segments. Choosing one of the segment is going to be done with the help of the A19, A18, A17, A16 lines. So in this construction, we have seen the bit combination. Try to note down this bit combination. See ma, whenever you would like to know what is the address range which is allocated for so and so memory device, or what is the address range which is occupied by the so and so memory device interface to the microprocessor, first what you are supposed to do means you are supposed to write all the 20-bit address lines, all the address lines like this, all the address lines like this. And how many address lines are directly interfaced to the memory device? They should be varied from the minimum to maximum bit position. They should be varied from the minimum to maximum bit position. Okay now, and this memory device is going to be enabled, means this memory device is enabled only when chip enable signal is enabled. In order to enable the chip enable signal, y naught should be enabled. In order to enable the y naught, we should have the proper input combination, and this is going to be decided based on the input connection, based on the connections made over here. So based on the connections made over here, A19 to A16 position, bit position should be always 0, should be always 0. Now in order to calculate the address range, what I am going to do means I am going to split this address bit positions into the nibble format. I am splitting this one into the nibble format because I would like to know what is the address range. Okay, so we know that 4 zeros is nothing but what ma? 4 zeros in the 16 in the hexadecimal format. 4 zeros is nothing but 0h. Is it on? 4 zeros is nothing but 0h, and another 4 zeros is nothing but 0h. 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 Okay, but the memory is varying from minimum to maximum combination na? So this is always fixed amount because the connections are not changing. As the connections are not changing, these bit positions are always zeros. These bit positions are always zeros. So minimum combination is over. Maximum combination is the, what is that? All ones. In this nibble, all ones means it is the f na, f h. Okay now, this one is going to be no need to write every time h. This nibble is also the 4 ones, means it is the f. This nibble is always also the 4 ones, means it is the another f. This nibble is always the sorry, it is not always. This nibble position is always sorry, it is not always ma. Obviously it is always because minimum we are taking from the minimum to maximum na. So this nibble is also 4 ones na. So it is the f. It is the f. Now the address range which is allocated for the device is a 00000 5 zeros to, here also we have the 0 ma. It is not changing, right? In the maximum combination also it is not changing, 0h. So the address range which is allocated for this particular memory device is going to be 50h to 0ffh. 50h to 0ffh. If you want to know that one, let's see the next slide. This is what the address space. This is the address space. Sorry, it is a 5f's are there na. Sorry ma, it is not the 5f's actually, it is only the 4f's. So address range is 5 zeros to 0ffffh. Are we clear? So for this particular interfacing diagram, this memory device is mapped into the first segment. Okay now, for this diagram, let us suppose if I am changing the diagram, means you may change, as I told you, you can change the output, you can choose any one of the output line of the address decoder to enable this particular device now, I'm changing the address line. So in this case, the output is the Y3. Okay, so Y3 means the combinations are going to be changes. In order to choose the Y3, obviously you are supposed to apply the 0 1 1 combination. You are supposed to apply the 0 1 1 combination. Okay now. So which means if you are sorry, in this case, in order to enable the chip enable signal, the rest of the concept is same, but here the connection is changing na, from the Y0 to Y3 it is changing na. So obviously input connections should be, in order to choose the Y3, the input combination should be what? Input combination should be the 1 1 0. You are supposed to apply the 1 1 0 as an input to the A16, A17, A18 or ABC input lines. Okay now, as I told you that you may map this particular memory space into the initial segments, or you may map this one into the final stage segments now. Me final segments, that is done based on the A19 position. If you are using the A19 to activate the active low signal, it is mapped into the first blocks, and if A19 is connected as an input to the activating high signal, then this memory space is mapped into one of the lower last, that is the final segments, that is the last segments in the order. Okay now, so for that also we have the interfacing diagram. Look at this. It purely depends on my interest. I may use the A19 over here, or I may use the A19 to activate the G1. It purely depends on your hands. Okay now, so no need to by this one. No sir, we are unable to remember the what is the address range, all those things. Then you are supposed to by the diagram as well as the what is that address allocated for the address range allocated for that particular device. But if you are following the rules, then it is very easy. Actually, I don't have the board. If we would have the board, then we would have seen different types of explanation, but this is what I made in the video format. Okay, so even you can change the connections. Means in this case, I'm connecting the Y7 now. I'm using the A19 to activate the active signal, and two active low signals are there now. They are directly connected by connecting that one into the ground signal, because it is a 0 volts. So A19. So in order to choose the Y7, A19 is always the one. A18 should be 1. Means we are supposed to give the 1 1 bit combination. Three ones are there at the input. Then only Y7 is selected. Then only Y7 is selected. Okay. At that time, this memory device is mapped into the last segment, because the higher nibble is a 1 1 1 1. Okay, now 1 1 1 1. Four ones are there. Because of that, this memory device is mapped into the last segment block. Okay, so this is all about your mapping the memory devices into the memory space. Mapping the memory devices into the memory space. We have one more also. Means here we have taken the 64 KB. Let us suppose I would like to interface. See, uh, what I told you that I don't know how many of you realize that this is a virtual realization. Means virtually microprocessor assigning the some memory space. Na, it is a what is that? Uh, this is a 1 MB memory space. In order to give the virtual division, I took this one. In general, the interfacing diagram looks like this. So in this case, I would like to interface the 32 kilobytes of memory. So when you would like to interface the 32 kilobytes of memory, how many address lines we require? We require the 15 address lines. So A0 to A14 lines coming from the microprocessor directly interface to the 32 KB. Means up to A14 are over. How many address lines are left, ma? 5 more address lines are left. Out of 5, sorry, out of 5 out of 5, in order to enable this particular chip enable signal, we are supposed to use one of the address decoder output line. So here I am using the output address decoder output line. So after allocating 15 address lines, whatever the remaining address lines we have, after allocating the 15 address lines A0 to A14, whatever the address lines we have, they should be used in the order. Okay now. So in this case, the order is the A15 should be connected to the LSB and A17 should be connected to the C. There is a rule, ma. So when you would like to interface the memory device to the microprocessor, first you should focus on how many address lines required by the memory device directly. All those address lines are directly connected from the microprocessor to the memory device directly. Okay now. And remaining address lines are used to as an input lines to the address decoder, as well as control lines to the address decoder, as well as control lines to the address decoder. So after allocating the 15 address lines, we left with 5 now. So these five signals, out of these 5, three signals from A15 to A17 are used as a input lines to the address decoder, and I am going to use A19 and A18 to enable the activating signal, like this. Okay, I thought it is the, yeah, here I have to type this one. Okay, so here after A17, how many address lines we left? A19 and A18 na? So what I'll do is I'll connect. It purely depends on my interest, ma. It purely depends. So you may use the A19 to connect over here, or you may use the A19 to connect over here. So depending on the bit position, the address space mapped means the address range which is allocated for this particular device is going to be varies. Okay, so here what I'll do is I'll make use of A 18. I'll go in the order. Okay, now for as a initial class, it is for simplicity. I'm going with the A18, and after that I'll take the A19 over here. A19. So this is another kind of interfacing diagram. With this interfacing diagram, the 32 KB space is mapped into one of the block provided by the 8086 microprocessor. One of the block provided by the 8086 microprocessor. So this is all about your mapping the memory devices into the memory space provided by the microprocessor using the address decoders. Okay, so this is only for this. If you realize this concept, then the interfacing diagram from your wait a minute. The interfacing diagram from your textbook as per your syllabus. As per your syllabus, I think it is taking some time. Oh, it's a 57 minutes more. Okay, if you realize that video, whatever the slides which we have seen over here, if you realize this one, then you will continue with the actual scenario. Okay, that's all for today's class.